Welcome to Chem 1B, Experiment 10, Thermodynamics of calcium hydroxide dissociating. Our goal is to come up with some data to generate a graph. The graph has an equation of the line. There is meaning in the equation of the line. The slope contains the enthalpy of dissociation, which we can determine experimentally and compare to literature in our post-lab. And the y-intercept contains the change in entropy for this dissociation. So we're going to generate data, use Excel or another graphing program to make a graph, take the slope and the y-intercept to solve for some values, and then compare to literature with a percent error. So calcium hydroxide dissolves and dissociates a little bit in water. And as the temperature goes up, it dissolves and dissociates a little bit less. And so what we're going to do is collect a KSP for calcium hydroxide at several temperatures, and then use that to come up with our X and our Y axes for data points. So 1 formula unit of calcium hydroxide dissociates to make 1 calcium ion and 2 hydroxide ions. And the thing that we can measure easily is the hydroxide concentration. When we find the hydroxide concentration, we recognize it equals 2 times the solubility. So divide it in half, come up with the solubility, plug that in our K expression to come up with a KSP for calcium hydroxide in pure water at several temperatures. So to generate, So here's an example of a titration. We're going to collect, Stu's going to show you how to collect and process a sample, but it'll be a 5.00 milliliter aliquot of the supernatant, the solution above the calcium hydroxide. And I'm pretending that it required 19.38 milliliters of strong acid, hydrochloric acid. And so I take my milliliters of hydrochloric acid, I convert it to, moles of hydrochloric acid. I recognize the 1-to-1 stoichiometry, and I have moles of hydroxide contained in that 5 ml sample. We have the molarity of hydroxide at this temperature. We can solve for what the solubility is, plug the solubility into our K expression, and come up with a KSP for calcium hydroxide at this temperature. Once we've collected all our KSPs and we know the temperatures, we can take the natural log and compare it to 1 over the temperature in per kelvins to come up with our graph. How does that work? Well, there's 2 important equations in this chapter, and one is I can find out, is this going to be spontaneous? Is delta G negative? By comparing the delta G from the book value to our actual conditions, which would be Q. And we know that the place that delta G goes from being negative to positive, not spontaneous to spontaneous, spontaneous to not spontaneous, is through 0. And that's the place where the relationship is in equilibrium. So when delta G equals 0, Q equals K, we come up with this equilibrium equation. Rearrange to solve for delta G of solution. And then we're going to set that equal to the delta G of solution of the other important equation in this chapter. We know that we can take table values for the enthalpy and change in entropy, and at a certain temperature in Kelvin, solve for, is this positive, 0, or negative? When it's 0, it's because we're in equilibrium. So we set these delta G's equal to each other and do a little bit of rearrangement.